The Earth's geomagnetic field is generated by the turbulent motions of liquid iron and nickel in its outer core, a phenomenon often explained by the dynamo theory. In this deep, high-pressure environment, the convective flow of electrically conductive molten metal creates currents that produce magnetic fields. Some scientists have drawn parallels between the behavior of this liquid iron and that of a ferrofluid, a fluid that exhibits strong magnetic responses due to suspended magnetic particles. Although the Earth's outer core isn't a ferrofluid in the traditional sense, it behaves similarly in that its liquid metal is highly responsive to magnetic forces. Could these natural magnetic responses be considered the basis for the geomagnetic field? Indeed, understanding these responses helps illuminate the complex interplay between fluid dynamics and magnetism deep within our planet. How do the convective currents in the liquid iron contribute to the magnetic field? As heat escapes from the core, it drives convection, which in turn creates swirling patterns of motion. These movements induce electrical currents that generate and sustain the geomagnetic field through what is known as the dynamo effect. Laboratory experiments and computer simulations have shown that even subtle changes in the fluid's flow patterns or composition can alter the strength and orientation of the generated magnetic field. This leads to observable phenomena such as geomagnetic reversals, where the north and south magnetic poles swap places over geological time. How might slight variations in the iron's properties influence these dramatic events? Researchers believe that the dynamic behavior of the core's liquid iron, including its magnetic susceptibility and the way it interacts with lighter elements like sulfur or oxygen, plays a key role in these periodic reversals. Studying the role of natural ferrofluid-like behavior in the Earth's core involves interdisciplinary research combining geophysics, fluid dynamics, and magnetohydrodynamics. Advanced computer models simulate the convective motions of molten iron, providing insight into how minute variations in temperature, composition, and pressure can affect the overall dynamo process. For example, researchers use high-performance computing to model how turbulent eddies in the outer core evolve and interact with magnetic fields over millions of years. These studies are not only crucial for explaining the current state of our magnetic field, but also for predicting future changes that could impact everything from navigation systems to the planet's protective shield against solar radiation. In essence, the investigation of natural ferrofluid-like properties in Earth's liquid core deepens our understanding of how magnetic fields are generated and maintained. While the outer core's behavior differs from man-made ferrofluids in key ways, its sensitivity to magnetic influences and dynamic convective patterns plays a central role in the geodynamic process. Could further advances in simulation and high-pressure experiments eventually unravel more details about the Earth's magnetic behavior? Ongoing research continues to address these challenges, offering the promise of a more comprehensive understanding of one of our planet's most fundamental phenomena. The Earth's outer core is composed primarily of molten iron and nickel, which behaves like a natural ferrofluid due to its liquid metallic state and interaction with Earth's magnetic field. The intense heat and pressure at the core create turbulent convection currents, which drive the motion of charged particles. This motion generates electric currents, which in turn produce magnetic fields through a process known as the geodynamic effect. The fluidic behavior of the outer core is crucial in sustaining the Earth's geomagnetic shield, which protects the planet from harmful cosmic radiation. Seismic wave studies confirm the existence of a liquid outer core with dynamic flow patterns that influence magnetic field variations. It is similar to a rotating pot of molten metal, where swirling currents generate electromagnetic effects, just like an electrical dynamo. The geodynamo effect describes how the movement of conductive liquid iron in the Earth's core generates a self-sustaining magnetic field. As the planet rotates, the Coriolis effect causes convective currents to spiral, creating helical motions that enhance field generation. This complex feedback loop ensures that the Earth's magnetic field remains relatively stable over geological timescales. However, periodic fluctuations such as geomagnetic reversals occur due to shifts in core fluid dynamics. Paleomagnetic records in volcanic rocks show evidence of multiple geomagnetic reversals throughout Earth's history, indicating variations in core fluid behavior. It is like a spinning bicycle wheel with charged particles flowing around it, generating a stable yet occasionally fluctuating electromagnetic field. Unlike synthetic ferrofluids, which contain suspended magnetic nanoparticles in a carrier fluid, the Earth's outer core is a homogeneous metallic liquid. However, due to the presence of iron and nickel, it exhibits magnetohydrodynamic properties similar to artificial ferrofluids. The core's behavior is influenced by temperature gradients, pressure variations, and interactions with the mantle. Understanding these natural ferrofluid dynamics helps scientists model planetary magnetic fields in other celestial bodies. Observations of Mercury and Jupiter's magnetic fields suggest that their cores may also exhibit similar liquid metal behaviors. It is like a giant rotating lava lamp of molten iron, where movement and heat variations shape electromagnetic activity. The Earth's magnetic field, generated by its natural ferrofluid core, acts as a protective shield against solar and cosmic radiation. Charged particles from the sun, known as the solar wind, are deflected by this field, preventing the atmosphere from being stripped away as happened on Mars. Without this protection, increased radiation exposure would pose significant risks to biological life and disrupt technological systems. The interplay between the core's fluid motion and electromagnetic forces ensures the continuity of this shield over time. The auroras at the poles, known as the northern and southern lights, result from charged solar particles interacting with the magnetic field. It is like an invisible force field surrounding a spaceship, protecting it from cosmic radiation. Heat generated from radioactive decay in the Earth's interior drives convection currents in the liquid outer core. These currents are responsible for the shifting intensity and occasional polarity reversals of the geomagnetic field. While the field remains relatively stable over short timescales, long-term changes can result in weakened magnetic protection, increasing vulnerability to solar storms. Studying these fluctuations helps predict potential disruptions to Earth's magnetosphere. During the Longchamp event, 41,000 years ago, Earth's magnetic field weakened significantly, exposing the planet to higher cosmic radiation levels. It is like a boiling pot of water, where swirling currents constantly change, sometimes creating turbulence and instability. Earth's magnetic field does not remain static. It undergoes reversals where the north and south poles switch places. These reversals occur irregularly, sometimes taking thousands to millions of years to complete. The process is driven by chaotic changes in the movement of liquid iron within the outer core. While a reversal would not pose an immediate threat to life, it could disrupt migratory animal navigation and technological infrastructure reliant on geomagnetic stability. The Brunches-Matuyama reversal, 780,000 years ago, was one of the most recent full polarity switches as recorded in oceanic crust magnetization. It is like a compass needle suddenly flipping direction due to changes in the underlying magnetic currents. Studying Earth's natural ferrofluid dynamics provides insights into the behavior of magnetic fields on other planets and moons. Some planets, like Mars, lack a sustained geodynamo, leading to a weakened or absent global magnetic field. This absence may have contributed to Mars losing much of its atmosphere over time. Understanding how liquid iron cores sustain planetary magnetic fields could inform future space exploration and planetary habitability assessments. Mercury, despite its small size, has a weak magnetic field, likely due to a partially liquid core with slow convection currents. It is like comparing different spinning metal spheres. Some generate strong magnetic effects, while others barely produce a field. Scientists use Magnetohydrodynamic (MHD) models to simulate the complex interplay between fluid motion, heat transfer, and magnetic field generation in Earth's core. These simulations help predict future geomagnetic variations and understand the effects of core-mantle interactions. Advances in computational physics and supercomputing have enabled high-resolution models that replicate real-world geophysical observations. However, modeling challenges remain due to the extreme conditions deep inside the Earth. Geodynamo simulations at research laboratories worldwide attempt to replicate the Earth's field reversals and long-term stability. It is like running a highly detailed weather simulation, but for the deep interior of the planet instead of the atmosphere. Despite advancements in seismic studies and computer modeling, direct access to the Earth's core remains impossible due to extreme temperatures and pressures. Innovative techniques such as analyzing seismic wave patterns and geomagnetic field changes provide indirect observations of core dynamics. Future missions may rely on deep Earth exploration technologies or novel materials capable of withstanding core-like conditions. Understanding the core's behavior is essential for predicting long-term changes in Earth's magnetic environment. The recent discovery of a potential inner core suggests that Earth's core structure is even more complex than previously thought. It is like trying to study the inside of a planet-sized furnace using only the sound waves that pass through it.